Hello, everyone. I guess it's been a long day, so thank you all for joining in. My name is Hamid Akhtar, and I'm part of Percona's Postgres engineering team. Today, I'm going to talk about Postgres replication and discuss some of the conflicts that may come up during replication. So, Percona not just has its distribution for Postgres, but we also have Mongo, MySQL, and we have a management and monitoring tool, PMM. So a lot of stuff, and all of it is open source. No closed source tools at Percona. A bit more about myself. So I've got more than 2 decades of professional software development experience in different industries and tools and technologies. I've been with Percona for more than a year now, and one of the things that stood out for me was an amazing work culture here. Very warm, very welcoming work culture. Prior to Percona, I was part of Hygo, which is a Postgres company working on foreign data wrappers and some in-memory access methods there. And before that, I was with Enterprise DB, working in the configuration management team. And one of the core responsibilities of that team was to create and publish the Postgres one-click installers that you may have used. In the past, we used to have those installers for Linux as well and other platforms, but now it's just limited to Windows. And also, very occasionally, working with DevRim for RPMs. So a lot of stuff there around Postgres. In case you need to reach out to me, here's my email address, LinkedIn, and Skype. I'm more active on LinkedIn, so please feel free to reach out to me in case you need to discuss or if I mess up anything during this talk. Percona has one of the things it has is an open community forum where you can come and discuss anything, whether you have a support contract or not. You can still come and discuss, and people would just try to help out in their best effort. So one of the things that you'll hear from Percona a lot, specifically around Postgres, is PGConf. That's an extension, a query observability extension, which is kind of like an enhancement of PGStat statements, but in a very different context, and provides insights into queries from a very different angle. Our GitHub is open. Feel free to just check it out and see. No strings attached, open license, no closed source at all. Some initial thoughts. Like any other solution, replication requires that you set up with an optimal configuration. So no surprises here. So you start with an optimal configuration, and then you allow the entropy to degrade that performance over time or that system. From a database perspective, that's queries that come in that change the state and cause sluggishness either in performance or cause other issues. So it's from that optimal or that tuned configuration, you're kind of then degrading ever to a lower performant setup. So it's really important that from that perspective, those queries are monitored, what they do, and why are they doing certain operations, and whether they're living beyond a certain predefined or expected age. Postgres has a lot of statistics available. I think it has more than in version 14, it has more than 50 views and catalogs. So a lot of information, a lot of columns, a lot of details. Stat statements, I think, has like 34 columns, all numbers mostly. So a lot of data to be analyzed and understood. So it becomes really challenging at times to ensure that you're stitching up a picture from all those statistics together. So once that system is done and it's up and running, it's really important that you understand the risks. And this is really part of this talk is going to focus on some of those risks in the replication side of things. I'm going to discuss streaming replication, and I'm going to deliberately avoid a logical replication discussion. So The outline of this presentation, so we're going to start with some initial discussion around locks. And we'll see why they're important, the concept of wall. Again, this is a little basic, but still just building up the story. We're going to see how replication got implemented in Postgres then. And finally, digging into the different type of replication conflicts. Before trying to understand under the hood how the Postgres server identifies that conflict internally, what it does, and how it attempts to then sort out the replication conflict. So locks from an internal perspective, you have lightweight locks, and then there are even lighter versions of that. Starting with the spin locks. So there are 3 types of locks that we're really concerned with. Spin locks are really busy waiting locks, and they're meant to be acquired for a very short duration for a few instructions really, or a few dozen instructions at most. They're implemented, if available, through hardware test and set instructions. So you can imagine that they're meant to lock for very short duration, and hence the busy waiting is fine with these locks. There are no niceties with these locks. So we expect to acquire them for a very short duration and release them pretty quickly. So niceties would cause significant overhead. So there are no deadlock detection. There are no release on error. So you expect that all of this is done by the calling process. And they're acquiring it for a very short duration, either just setting up, updating a variable or a few variables. So not a lot going in here, no real operations. Then there are the lightweight locks. Now we're gradually kind of increasing the duration for which a lock can be acquired. Spin locks were for shorter duration. Lightweight locks are required for a little longer. And hence, they are really there to manage the access to internal data structure and do certain operations, which means that you can hold this lock for a little longer. So with that additional responsibility, or with that additional time that you have for these locks, you can basically, there's some niceties that come in. One of those is automatic release on error. So that's one thing. Deadlock detection is still not part of these locks because, again, these are meant to be for shorter duration. Just to put the perspective in terms of when I say duration, spin locks are meant to be acquired for very short duration with a max timeout of 1 minute. And that's like an infinite amount of time for those locks. Lightweight locks can take a bit longer or significantly longer. So whereas the spin locks were busy waiting, these are actually dependent on system semaphores. And they're actually, so if a queue builds up, they're acquired or released based on the arrival order. There was some concern in terms of whether the read-write locks have a separate queue and the shared ones have a different queue, and there is a prioritization in between. But I think there are a few threads back in 2018 and somewhere there around those. I've not dug into more detail around these. Finally, we have the heavyweight locks. So these are the regular locks that are basically, from a user perspective, managing all the controls or table-driven semantics. So they're controlling all of that. They have deadlock detection. They're contained with the resource manager. And effectively, these are the locks that will cause the conflicts for us in replication. The potential for other lightweight locks, but these are the ones that are going to be, can be managed, or somehow the risk can be mitigated in some form through configuration. Write-ahead log, so replication is all about catching up. So standbys are always playing catch up with the primary. So they're trying to get hold of these, the data on the primary and trying to update themselves with that. Write-ahead log was introduced in version 7.1 in 2001. So it's been around for a while now. Prior to this introduction of WAL, the transactions were actually writing the transaction details or the dirty pages onto the disk through a system call. So which meant that every transaction was dumping their pages, and that was obviously leading to a significantly slow performance and response time. What write-ahead log is doing is actually keeping a track of changes and actions that are being done. And this, in a way, provides durability, but a stronger guarantee of durability that was previously done through the processes writing that dirty page onto the disk. So I'll explain why this has a stronger guarantee than that. In version 9.6 and below, it was called PGXlog, and a lot of people, including myself, love to delete log files, and people accidentally end up deleting the wall files. So version 10 and beyond, it's called PGWall. So that's an improvement, a better user experience, I guess, for some users. And in the code, there's still a lot of references of Xlog, so don't be surprised if you come across that terminology. It's not just about relations, but it's also about indexes. So anything that requires persistence, so wall in terms of data, that's where wall comes in. As I said, it improves the performance significantly and response times significantly as well, because now, rather than spreading the writes being spread across multiple files, they're being written into one file, really. So the dirty pages, rather than being dumping the whole dirty page, now you're keeping a track of those transactions in a form of wall record. So smaller data being written quicker, more better. So response time improves significantly here as well. Internally, so the wall files are being part of recovery as well, and point-in-time recovery, and PG control file contains a lot of that information for us. So one of the things, when I said on the last slide that it ensures durability, a stronger guarantee of durability, that is done through full page image writes. Immediately after a checkpoint, a dirty page is dumped onto, when a page is updated, it's dumped onto the wall file, basically, if you have it enabled, if full page image writes are enabled. Now, this allows, in very rare cases, an 8K page being corrupted. This allows us to track back and ensure that the transaction that was previously committed, we have some way of recovering from that loss. Wall file name always looks complicated, to me at least, used to. It's a 24-digit number, a hexadecimal number. So, and it can be broken down into 3 components. The first 8 digits refer to timeline. The next pair of 8 is really the wall file. And the wall file segments. A wall file segment is, by default, a 16 MB segment. So that's where you have the 16M coming in. And then if you want to differentiate between a logical wall file and a physical wall file, so a logical wall file is basically the 8 digits in orange, which comprise of about 4 GB of data, 4080 megabytes to be precise. And that's where those calculations are coming up, and that's how these numbers are incremented. Not going into those specific calculation details here. LSNs or log sequence numbers is what you'll come across when looking at replication, especially lag, and all of those things are defined in terms of LSNs. LSN is really the location within the log file. So you can exactly point out where a particular wall record is. The data type that's used in PG is PG LSN. That's an 8-byte or a pair of 2 4-byte numbers. And they're separated by a slash. So you can see, for example, the current insert LSN is 0 hyphen and then the hexadecimal number. You can see where this particular LSN resides within the wall by using the PG wall file name function. Further to that point, you can also see exactly where in the wall wall file this record lies by adding _offset to this function name. So that's another option where you can see exactly where that resides. And you can actually see, if you execute a transaction, you can see how those values or those offsets are incrementing. So you can understand the kind of load that's being written. Digging into the replication in Postgres. So some of the history. The first traces of replication can be tracked back to 1999, where the replication was actually implemented. But that was a very different implementation to what we currently have. The current implementation can be based on the log shipping implementation of 8.2, which was basically based on the wall implementation. Wall, remember, came in 2001. This was 2006. So 5 years after that. It brought in the concepts of continuously archiving and continuously recovering. The archiving part was done on the primary server, and the recovering part was on the standby. This was a file-based log shipping, so which meant that we weren't really streaming or sending out individual records, but those records were actually being accumulated, and the file was being packaged before it was being shipped. The consideration really was about bandwidth here. There was a configuration parameter of archive timeout. That could be, if that timeout's early, the wall file gets shipped early. But the challenge here was this was asynchronous, because the primary was holding some data that may not have been shipped to the standbys. So, which meant that this asynchronous process can lead to data loss. Because if the primary crashed and it still had some records that were not shipped out to the standby, this was basically going to cause data loss. But this was more of a disaster recovery replication setup rather than a high availability. So, yeah, OK. So from warm to hot. So warm standbys were not able to accept or honor read queries. The standbys, the hot standbys could. With 9.0, this was a major enhancement, and in 2010, streaming replication came in. Now, the streaming replication concept was of two new postmaster processes. There was a wall sender and a wall receiver. The wall sender was on the primary server, and the wall receiver on the standby. The responsibilities were pretty clearly defined, with the wall sender responsible for flushing or streaming the wall files to disk on the primary server, and then also shipping out to the standby. The wall receiver on the standby was responsible for taking in those wall files and then basically streaming them onto the disk. So the new two processes also brought in two functions. So these were the first functions for monitoring replication in Postgres, really. Receive xlock location and the replay location. From receiving, the process of receiving a wall file can be broken down into 3 steps. You receive a file, you basically write onto the disk. When I say receive it, it's more like writing onto the disk. And then you, that writing onto the disk has 2 steps. One is writing in the buffer, and then getting that data flushed onto the actual disk. Remember, there is going to be some disk cache that's going to be right up there, and that could possibly cause data loss if the data is written into the disk cache and there is a abrupt termination or server shutdown for any reason. There can be some battery-backed units, but that's a different story. But the challenge with this was it was still asynchronous, so data loss was possible. Although the difference now was that this was around 1 second delay from actually on the primary and then having it on the standby, but still the potential was there. So immediately in the next release, 9.1 brought in synchronous streaming replication. So this was basically a performance versus a data integrity trade-off. When you say it's synchronous, that means that the primary and the standby have to be in sync, which meant that a commit confirmation message can only be sent out once that transaction is actually there on the primary server, as well as that wall file has been received by the standby. So, which in turn obviously brings in a bit of delay or slowness. There were a lot of new configuration parameters with Synchronous setup. So you could set quorums, you could set priorities, you can specify whether, say, any of the 3 or any of the 5 standbys, synchronous standbys should receive or send out confirmation, or we should wait for their confirmation. So there were a lot of configuration options that you could play around. So not necessarily having to kind of work with a fixed set and depending on their confirmation before a transaction can be confirmed. So decoding of wall replication was introduced 9.4. This is not really relevant, but I thought it was worth adding a note for this. Looking at the replication catalogs and views. So with reference to this talk, I think the relevant ones are PGstat replication and PGstat wall receiver, and then there's one more that I'll discuss on the next slide. PGstat replication has one row per wall sender process that's connected, so for connected standby. So every standby that's connected to the primary server has one row here. While config, so what it provides is application information, and it provides some details about how those wall files are being received, whether they've been written on the standbys, whether they're flushed, whether they've been replayed, where exactly in terms of LSNs that standby is. Also, there are timestamps. This is actually a join between PGstat activity and another function, which means that this data is not persistent. PGstat activity does not persist that connection information details. So no persistence here. That information will go away the moment that connection or that standby disconnects. Then you have PGstat wall receiver. Now that PGstat replication is a view that's available on the primary server. Standby has a wall receiver which tells about similar statistics, the connection information, and some other details, but additionally it also has replication slot details. In terms of conflicts, so PG has just one real view, PGstat database conflicts. And it's a very simple view with not a lot of details. All it has is dat ID, dat name, and 5 big N counters to count 5 different kind of types of conflicts. And that's really all that it tells. The PGstat database also has a column named conflict, and that's just a big N, and that's just a counter. So no real information around conflicts that will help understand when the last conflict happened and any other details around that. So, looking at some of the configuration parameters, as you can see, there's tons and tons of configuration parameters, and that's why replication becomes a challenge, because these are somehow interlinked in some way or form. So looking at some of the important ones, you have max wall sender. This is effectively one, you'd want to set it at least, so one standby would actually have one connection, so they'll consume one wall sender. But you'd also want to account for any wall sender processes that may get orphaned by a standby that gets disconnected or a network outage, so that wall sender may remain alive until there's a timeout that occurs. So this value needs to be a little higher than the number of standbys you expect. Wall keep size is a very important one, and it's kind of at the core of replication. This, by default, is a value in terms of size of the wall data that needs to be kept or preserved by the primary server to ensure that replication on the standbys can be tracked. so they can follow the primary. It's by default in megabytes, and the moment this value, the moment a standby lags behind this value or goes behind this value, say if you have by default a 10 MB wall keep size and a standby is expected to now get 15 MB of data, then it's already too late for that standby. And because the primary has already removed the required wall segments and may have removed those wall segments, which means that there's no way for it to catch up with the primary, and the connection would get terminated. Wall sender timeout is a timeout on the primary where, or on the sending server where a connection, replication connection that's not alive or not being able to respond for this would get terminated. The key terms that you might have noticed here are sending server, primary, and standby. The differentiation is that, well, although primary server and standbys are pretty self-explanatory, a sending server is a server that's passing on the wall files to another standby. All primary servers are by default sending servers, but additionally in cascade replication, you may have a standby that's shipping on some wall files to other standbys, so that becomes a sending server. Primary server has a couple of key configuration parameters. You have synchronous standby names. That's something we've already discussed. And then in terms of priorities and quorums and the configuration that you can set with standby names. Vacuum differ cleanup age is a configuration parameter that dictates how long should, or in terms of number of transactions, how long should vacuum or hot updates wait before cleaning up dead rows. So this plays, again, a very important role. We'll come to that in a bit. Max standby streaming delay is effectively a value that by default it's 30 seconds. That's when the wall receiver process on the standby will wait for this much time before it starts generating the conflicts or triggering the conflict procedure. We'll jump on. So replication conflicts, but in a simple replication environment where we have one primary and a lot of standbys, where would a replication conflict come in? We have one server that's accepting write queries. All others are accepting read queries only. So why would there be any conflict here? The conflict really comes in because on the standbys, you have a backend process of a higher priority. So you have a wall receiver process that's meant to do certain operation. It takes a higher priority than any user processes. So any queries that are currently being executed, the wall receiver needs a higher priority than those. And that's where the conflict comes in, because it wants to replay those wall files or wall records, and user-facing queries or some other queries are basically holding back those resources and not allowing it to take control of those locks or those resources. And that's where the conflict comes in. On the primary side, there are no such challenges. The MVCC takes care of this. And generally, the transactions are long-running queries, which are really the culprit in most cases here. So conducting an internal survey within Percona with DBAs and some of the users of Postgres, although the number of responses is just 9, but looking at the value, more than half of the people have experienced challenges with Postgres replication. And if I'm to weigh this number a little more or give it a little more weight, a couple of people never actually worked with replication. So this number actually, in terms of percentage of people who worked on replication, is much higher. I'll give a few seconds to let this sink in. People have experienced all different kind of issues, whether that's replication lag or loss of wall files, or whether that's a problem with replication slots, or whether that's failover issues or slot missing after failovers. But the key ones that we're concerned with are the 5 conflicts from tablespace conflict, lock, snapshot, buffer pin, and deadlock conflicts. Those are the ones that are tracked by PGStat database conflict view. So the type of conflicts that come up are the tablespace conflict is basically related to temp tablespaces, which are used by temporary tables or indexes on temporary tables or for sort operations on large data sets. With that tablespace being dropped on the primary and still being used on the standby, that conflict will happen. However, this is not very common. How many times are you going to actually drop a tablespace? Buffer pin, again, it's also not so common. It's when the hot chain pruning process acquires or pins a page for pruning the hot chains. And that's where this conflict comes in. Again, that's very rare, not much you can do about it. Deadlocks are also not so common. What are more common are locks and snapshot conflicts. Lock conflicts arise from a process or a process still using or maintaining a lock on a relation, and the wall receiver trying to get an exclusive lock on that same relation or that index. Snapshot is when you're trying to access row versions of tuples which have already been vacuumed out on the primary, and that's where this comes in. Let's look at these 2 conflicts in a little more detail. So the environment that I used was Postgres 14.1 on CentOS 7, simply creating one primary and one standby, and generating conflicts on those. Generating a lock conflict is actually rather simple. Creating a simple table with 100 rows, beginning a transaction on the standby, selecting that relation, not really using any of that value, and then dropping that relation on the primary server. Waiting for max standby streaming delay, which by default is 30 seconds, and then querying or executing another query, and immediately getting a termination message because of conflict. The message is very precise, telling me exactly why my connection is terminated, because I was holding a lock on a relation for too long. One of the things that you'll notice is that I'm not really doing much in this transaction. I've accessed a relation, but I'm not kind of using it in any way. So I've queried it, but the data has been kind of not really consumed. So even in this query, the resource manager will track any relations that you've accessed, and it will maintain a lock on this relation. So looking at PGStat database conflicts, you can see that it has incremented the conflict for lock count to 1. So that's all that it will tell us that it's been updated. Again, this information is ephemeral, so if the server restarts or the standby restarts, this information is lost. There is no persistence here with this data. Looking at under the hood in terms of how Postgres actually tracks this. On the standby, we have the wall receiver process, which initiates a standby redo operation internally. Now what it needs to do is acquire exclusive locks in this case. So it tries to acquire exclusive locks, goes through a number of functions. There's a lot of code around this lock and resource manager behind the scene that's basically walked or gone through before. It ends up waiting on the lock. That wait is defined by the streaming delay that we've seen previously. So what it does is that it identifies the backends that are conflicting, that are not allowing it to acquire that lock or the locks that it intends to. So it prepares a list of those locks. And once that timeout has completed, it then generates a termination message, sends out that termination message to all those backends with a very specific message about lock conflict. So it's basically an enumeration or a value, but the backend knows what that value translates to, and then it gives user a very specific error message. How can these be potentially avoided? In terms of, I think it's also about understanding your workload. But you could, for example, monitor PGStat activity and PG locks. You can join them together based on PID and then track which queries are holding locks beyond their expected duration. So any connections or any transactions that are there for much longer, they're basically the culprits here. Generally, you'll see in most observability or most performance-related issues, the long-running queries are at the core of those problems. So any transactions that are aging beyond their life, any connection, or any of those details, you can track them through stat activity and then joining locks. The other thing that you can do is maybe look at max standby streaming delay. The default is 30 seconds, whether you want to increase it. Remember, there's going to be some side effect once you change that. But whether your queries are really expected to run for more than 30 seconds, and whether those exclusive locks that are being acquired have on relations have a higher frequency. So, and also it's about optimizing your queries, whether you're touching indexes or relations that you should not really be touching, whether they're just can be refined and reduce your impact around this. Looking at a snapshot conflict, a little trickier to generate. So creating another table and dumping 100 rows in it on the standby, starting with a transaction, declaring a cursor, and accessing that and fetching data from that cursor. On the primary, deleting some rows, and then issuing a vacuum. So it's a manual vacuum command. I'm not relying on the auto vacuum to trigger that vacuum process. So issuing that manual vacuum forces the standby immediately to generate a conflict when the next query is executed. It's not waited for the streaming delay here, because this is a manually triggered command. So no delay here. It wants to process or run the vacuum immediately. And you can see, again, a very specific error message with row versions that have been removed, and the transaction is trying to access that. Looking at database conflicts view, so it's incremented the conflict for snapshot by 1. So no real fun here. In terms of code, the way this changes is that after xlock function, it basically goes into the access method functions. So in this case, it's trying to perform a cleanup for the heap. Again, it'll try to acquire the locks. It will identify the backends, and in this case, it's not weighted because it was a manually triggered command. And immediately, it has terminated those backends. Again, with a very specific message, with a very specific enumeration that tells the backend that it's been terminated for what particular reason. The gugs that can play a role in this, avoiding this kind of conflict, is vacuum differ cleanup page. Remember that this deals with the cleanup in terms of the cleanup page in terms of transactions, whether we're dealing with the vacuum or whether we're dealing with hot updates. I'm not sure whether the version churn introduced in B-trees in version 14, the duplicate version churns, whether that has an impact here, or whether this, because it's very similar to hot chain updates as well, where the cleanup on a particular page happens. And then you have the hot standby feedback. It eliminates query cancels because of cleanup. What this can lead to is what this gug does is it provides the primary server with the feedback that it's there are certain transactions running on the standby. And even in case of if you have cascade replication implemented, that message from those cascaded standbys is channeled through to the primary. So there is a mechanism of still getting that information out. So some closing thoughts. So it's very hard at times to tune for a particular workload. There's no single solution that fits everything, but there are certain things that sits at the core, so certain configurations that need to be managed. Wall keep size is one critical one, which tracks the lag, but also the moment you tune some other configuration, whether that's replication delay, then you might also want to increase this value, whether that's the response time or that it effectively translates into maybe increasing this wall size on this primary. Yeah, remember that the information, a lot of this information is ephemeral, which means that any restarts will cause you to lose that information, and that will no longer be available. This is one of the problems that we've solved with PGConf, which kind of persists with this information, and even the information that's there with stat activity, it kind of persists that information for much longer. Long-running queries are really the enemy, whether you're dealing with bloats, whether you're dealing with performance issues, or whether you're dealing with replication. That's all. Thank you, everyone. Thank you so much. Any questions? Please feel free to.
Hi. If you have questions, please do wait until I get to you with the microphone. So just raise your hand and I will scurry to you. Who's first? A resounding success. You were so clear and so thorough that nobody has any questions.
Yeah, maybe I've caused them to sleep through the presentation. So it's either that or that. Thank you, everyone. Thank you, people.